Hola, Buenos Aires. Soy Dave Aronson, el T-Rex de Codosaurus, y estoy aquí para enseñarles sobre algoritmos genéticos, pero lo haré en inglés, mainly because I don't speak much Spanish, as you may have guessed from messing up soy versus estoy. Anyway, what are genetic algorithms? They are shortcuts to find a good solution to a problem. And heuristics like this are good because they are faster, simpler, cheaper, or in some such way less resource intensive than methods like precise calculation or brute forcing your way through all possible values. However, heuristics are not guaranteed to find the best solution, just something good enough for whatever value of good enough we care to apply. The way genetic algorithms in particular work, as you may have guessed from the name, is inspired by real-world biological evolution, primarily the principles of survival of the fittest, random combination of different sets of genes into one new set, and random mutation. The history goes back to 1950 when Alan Turing, as in Turing test, Turing machine, Turing completeness, the ACM's Turing Award, and so on, proposed a learning machine in which the mechanism of learning would be similar to evolution. However, it didn't really catch on. Simulated evolution as a general approach wasn't really popular. Well, it was never really popular, but it didn't catch on much at all until the 1960s and 70s. It is still occasionally seen in the wild, though. Most famously, in 2005, the United States National Aeronautic and Space Administration, NASA, used a genetic algorithm to design an antenna for the ST5 series of satellites launched in 2006. The Jet Propulsion Laboratory website says, its unusual shape is expected because most human antenna designers would never think of such a design, and that's one of the great advantages of this approach. However, today we'll only be looking at much simpler problem domains, ones where we actually could think it up, but they make a decent demo. The process of a genetic algorithm is a simple set of steps. First, we create an initial population of individuals. In genetic algorithm lingo, these are called chromosomes. But since most living organisms contain lots and lots of chromosomes in every cell, I don't like that term. I think it leads to confusion. So I'm just going to say individuals. The next step is to assess how fit these individuals are, according to whatever criteria we want to apply. Next, we ask, are we done? If not, then next we select some individuals to breed the next generation, actually do the breeding, creating a whole new population, mutate those new individuals, and then go back to step 2, assessing their fitness. This could be represented at a high level with some rather simple code, like so. Now let's take a closer look at what goes on in each step. First, we create a population of individuals. But what are these? They are different solutions to some problem, usually represented as different instances of the same data structure, like objects of the same class, maps with the same keys, or anything else we want, so long as they can be evaluated to come up with a fitness score, and we can combine 2 or maybe more old ones to make a new one. Suppose we want to evolve a good set of character stats for a Dungeons and Dragons fighter character. So our individuals in this case would be sets of stats. Now, my D&D knowledge is a little out of date. I haven't played in about 30 years, but back in my day, character stats were strength, intelligence, dexterity, constitution, wisdom, and charisma, each determined by rolling 3 six-sided dice. or 3d6 for short. And I'm going to just gloss over how you can sometimes have extra strength. In code, we could represent these as a class in a language such as Ruby, like so. Defining the roll function is left as an exercise for the watcher, but it's pretty obvious what it's supposed to do, and it's pretty easy to implement. To create an initial population, we can just create a bunch of individuals, however many we want, and stuff them into an array like so. This could actually be done in much more idiomatic Ruby, so don't scold me for that, but I'm trying to keep it understandable by people who don't know Ruby. So if we create an initial population of 10 characters, we might wind up with a list like this. The next step is to assess how fit each individual is. In other words, each of these characters, how fit they are as a fighter. And we do this with what's called a fitness function. Just like how biological creatures might be perfectly fit for some particular environment, but a lousy fit for another, our fitness function should reflect how fit an individual is for some particular purpose. Now, we're trying to evolve a good set of fighter stats, so it should be based mainly on strength and constitution. Dexterity is also helpful, but intelligence, wisdom, and charisma, not so much. But we don't want them too low for the sake of occasional saving throws. I toyed with a few different things, such as totaling up double the strength plus the constitution plus half the dexterity, but the other stats tended to get too low, and even the dexterity was tending rather low. So I tried prioritizing them linearly, adding up 6 times the strength, 5 times the constitution, and so on down to 1 times the charisma. But then the other stats got too high and the characters seemed too generalized. Eventually, I settled on this, prioritizing the stats much more strongly with powers of 2, totaling up 32 times the strength, 16 times the constitution, and so on down to 1 times the charisma. We could get as complex as we want in this function, and NASA's antenna fitness function certainly must have been. Even though the fitness function itself can be very simple, it can be difficult to figure out one that will yield good results. If we run this one on our current population, we get this. Now that we know each individual's fitness, the next step is to see if we're done. So what are our criteria? Let's say we're done if any individual gets 90% of the way to the maximum score of our fitness function. The maximum score is 1,134. So 90% would be 1,021 after rounding. In code, that are we done function would look like this. As usual, we can get as complex as we want with all kinds of other stopping criteria, like checking if the maximum average or minimum fitness is not improving, or some number of generations, or some amount of time, or if the user presses a stop button, or many other parameters, or a combination of them. Anyway, none of our current individuals score anywhere near 1,021, so we go on to the next step, which is to select some individuals to use in breeding the next generation. The obvious way is to take the top 2 scorers like so. We take our current population, sort them by fitness in descending order, and take the first 2. With our current population, that would be these 2. Again, we could get more complicated, like selecting 2 randomly, with each individual having a chance to be selected proportional to their fitness, and lots of other ways. We could also take more than 2, whether to breed all pairs in that set or to combine more than 2 at once. We could even combine such strategies, like using all trios from a randomly chosen 5, with the fitter ones having a better chance to be chosen. Anyway, now that we've chosen our breeders, next we actually breed them. And the usual way is called crossover, and consists of taking data from one parent up to some randomly chosen crossover point, then switching to take the data from the other parent. And this can be extended with multiple crossover points. Another common way is to decide randomly which parent contributes which part of the data, or in genetic algorithm lingo, which gene. And that's what we'll do here, like so. You go through the stats one by one, flip a coin, which we used to call rolling a D2, and if it comes up 1, we get that stat from the first parent, else we get it from the other parent. Oops. That gets us a result that might look like this. In this example, this new character got the strength and intelligence of the first parent and everything else from the second parent, which is the same as if we were using the crossover method, with the crossover point being between intelligence and dexterity. This is just one of 10 results, because we're making a whole new population like so. This is almost identical to how we created the initial population, except that instead of each individual being made up from scratch, they're the product of breeding our 2 chosen breeders. And a whole list of 10 would look like this. You can see lots of family resemblance there. For each stat, there are only 2 possible values, or in genetic algorithm terms, alleles. That gives us a total of 64 possible combinations, even less if any stats were the same between the 2 parents. On average, you can see these look much more suitable as fighters than the previous generation, though we'll figure their actual fitness scores later. If we were to just continue breeding the fittest of this population and the next and so on, we wouldn't see any further improvement in the values of each stat. But we'll fix that in the next step, which is to mutate those individuals. Again, I'm going to keep it very simple and give each stat just a 1/3 chance each of staying the same, going up a point, or going down a point within the valid range of 3 to 18. In code, that would look like this. For each stat, we just add a random number from 0 to 2 and subtract 1, which is like adding a random number from -1 to 1. Again, we could get as complex as we want, like giving it a higher chance to go up or down, maybe by multiple points if it's very low or very high, to simulate the real-world phenomenon of regression to the mean. And we could add all kinds of other options. If we run this mutation function on our current population, we wind up with something like this, after coloring the stats that went up in green and down in red. You can tell at a glance there's a lot of mutation, and if you look at the values in each column, you can see now it's much more diverse. And now we go back to step 2, assessing the fitness of each individual in this new population. If we sort on the fitness descending just to make it easy to find the best ones, we get this. And now we can see for sure that this is much improved from the prior generation. The old one ranged from 476 to 760, and this one ranges from 635 to 851. It's still nowhere near our stopping criterion of 1021, though. So fast forwarding through 6 more rounds of selection, breeding, mutation, and assessment, we finally get one with good enough individuals, like so, with one suitable character having 18 strength and constitution, but unfortunately subpar dexterity, though not too horrible, and surprisingly high intelligence. If we really wanted it more specialized, we could complicate the fitness function again and do things like explicitly demand that it be well above average in all the character classes' necessary stats, so that 9 dexterity would just completely disqualify it, and maybe forbid it to be so high in the others, or at least apply a penalty, which in this case would apply against that 18 intelligence. Now let's suppose we don't need any more fighters in the party, but now we need a wizard. All we need to do is tweak our fitness function like so, to prioritize intelligence first, then wisdom, and so on down to strength. An initial population would look roughly the same since we haven't changed how that gets generated. So I'll spare you those steps. But after 11 generations, I got this, containing 3 individuals 90% fit to be wizards. They're mostly pretty good in the other stats, but not so much as to be obviously better suited for some other class, except that top one looks kind of like a bard to me. Remember, though, that this is all very random. It may converge on a good solution faster or more slowly, and the fitness function may be good or poor at getting just the right mix of alleles. Now, suppose we want to evolve something completely different. In my spare time, I make mead, or in Spanish, hidromiel, a wine-like drink made by fermenting honey. Let's see if we can evolve a good recipe. A recipe will be based on 2 simple factors: the ratio of water to honey and the alcohol tolerance of the yeast we'll use, both measured by volume. The more honey per volume, in other words, the lower the ratio of water to honey, the higher the level of alcohol you could potentially get if the yeast will tolerate that much alcohol. Any leftover honey that the yeast doesn't eat up and convert into alcohol is what makes the mead sweet. And these 2 resulting factors, the percent alcohol by volume, or ABV, and the sweetness, will be how we'll evaluate each recipe. We'll spare you the details of how we figure that out, though. Of course, we'll need a new fitness function. This one looks at how far off we are from our desired target values, and we square the error in each aspect separately so that something that's, say, 1 point off in each will score better than something that's spot on in one but 2 points off in the other. In other words, we want them both close, not just trading off one for the other directly. You can see here we're targeting 12% alcohol by volume out of a range of about 0 to 20, and 15 points of sweetness, which is on a sort of custom scale of 0 to about 80 for anything reasonable as a finished product. So we're going for typical wine strength and semi-sweet. Of course, there are other bits of code we'll need to change. For starters, the breeding and individual mutation functions will only need to take care of 2 stats rather than 6, just like the individual creation function. But the generic stat mutator and the calls to it from the individual mutator will be a bit more complex, as it needs to take different limits into account, including working well on differently sized numbers. What this one does is to multiply by somewhere between 81% and 119%. So it's got very little chance of staying the same, and the difference will usually be small because we're using multiple dice, so we have a bell curve. But it could go up to 19% higher or lower. Everything else, such as creating the initial population, selecting the breeders, breeding the new population, the concept of how to check if we're done, though now with a different threshold, and the overall structure of how it simulates evolution, all remain unchanged. To demonstrate how this one runs, an initial population might look like this, and the next generation might look like this. After just 7 generations, I got this, with a candidate weaker and sweeter than we want, but within our 90% fit criterion. If we get really picky and demand a 99.9% fit, my first run like that took 45 generations and yielded this, a tiny bit weaker and sweeter than asked for. And just like with the Dungeons and Dragons characters, if we want to change what we're after, all we have to do is tweak the fitness function. In this case, we could even ask the user for the numbers, but I'll leave that as an exercise for you. Anyway, I asked for 7% alcohol and a sweetness of just 5, a low alcohol dry mead, often called a session mead. And still demanding a 99.9% fit, it took 37 generations to get this, spot on in sweetness and just a tiny bit weaker. Then I asked for 16% alcohol and a sweetness of 35, a strong and sweet mead, historically called sack mead or a grape mead, a style very popular in Poland, the most mead producing country these days. It took 149 generations, which was still very fast because our functions were so simple, to produce this. Just a tiny bit stronger and drier than asked for. Now, just a little bit ago, I said that a lot of stuff was unchanged between these two usages, the D&D characters and the mead recipes. I usually wait until we have 3, but let's pretend we have a third one. And that would mean that we should extract those unchanged parts into something they could all use, something with a name like, say, Evolver. That's my actual license plate, by the way. I've had it for several years. With just a little bit of tweaking and a slight sprinkling of Ruby magic dust, we can extract a class that will take another class that defines the necessary functions and run evolution on it like so. And then our character and recipe classes can be shortened like so and like so. No, I don't expect you to read those, let alone remember them, but the final slide, which we're now at, has the URL for all the code plus the HTML and images for the slides, complete with script, which I've mostly stuck to. It's that last URL there, the one at GitHub. So that's it. Now time for questions.
Bueno, estamos nuevamente aquí en el track Nerd y tenemos a Dave Aronson para hacerle algunas preguntas, así que vamos a darle la bienvenida. Hi Dave, how are you?
I'm doing fine. How are you?
I'm good, doing well, thank you. So I'm going to give you like a couple of questions that the audience left. So, are you using another tool to analyze like the gene sequence?
In the construction of these particular examples, no, I was not using any other tool. I was deliberately trying to not depend on anything else to show how simple it could be. The only other thing used was just the stuff needed to run Ruby code. That's all. And just to be clear, Ruby has no particular advantage in this over any other language. You could do this in whatever language you choose.
Sounds good. So, what do you think about AlphaFold from DeepMind? Is there other way to apply sorry. My God, I kind of like I'm stumbling. Artificial intelligence in genetics?
It's an interesting question. One could certainly apply artificial intelligence to all kinds of things, including real-world study of genetics, all kinds of data mining one could do there. But as far as genetic algorithms, algorithms that are inherently mimicking genetics as opposed to being about real-world genetics, nothing's really leaping to mind, but one could certainly use perhaps genetic algorithms in order to evolve a good training set for a machine learning model or something like that. Any kind of data you want to throw at it that you can evaluate for fitness somehow, preferably very quickly, and that you can combine into a new version, you could use genetic algorithms on it.
Sounds good. So, do you have a place where we can find some more documentations on this? I know it's a wide question, but kind of like to guide people to start learning a bit about this.
Well, the main resource I used was simply Google. I just Googled genetic algorithms and saw, oh, that's a lot simpler than I thought it was. Yeah, I think I can put together a talk explaining it. So if I thought it was that simple, surely your audience should be able to understand it with very little problem, if any.
Sounds good. So, what sort of problems are genetic algorithms well suited for, and what sorts not?
The main ones it's suited for are ones where the data is relatively straightforward. The thing about a training set for a machine learning model, I think that falls more into the not well suited. The main criteria are that you need to be able to evaluate the fitness of each candidate or individual, whatever you want to call it, preferably very quickly. And you need to be able to combine two or more, if you choose, of them into one new one. So there's lots and lots of things. The canonical example is the knapsack problem, which is basically a constrained resource allocation problem. And anything that essentially boils down to that. The canonical representation of that is you have a knapsack and a lot of different things you could put in it, but you want to maximize the total value. And this can be represented as a simple string of bits. Each one is just, do you take this item or not? That's about as simple as data gets. So it's very amenable to combining them and evaluating the fitness, assuming that all you care about is the literal value of a set of items. If it gets a little more complicated, like you're trying to determine a national budget and you have a lot of trade-offs to deal with, that can get a little more complicated. But when the data is very straightforward, that's a great fit.
So, why do both combining and mutation?
If you combine them, then you may get a different mix of alleles from each parent, as shown in the example where I said, this character plus this character wound up giving you this character. But if you don't do any mutating, then you don't get any different alleles. And you wind up with, in the case of the D&D character, only 64 possible values. If you let each one go up or down by a point, then you've basically tripled your number of alleles you can have in each column. And let me just do some quick math. I think that would mean like 3 to the 6th, whatever that is, more possibilities, more possible combinations. So you get a lot more biodiversity if you want to continue stretching the analogy. So you may wind up with something much better than could have been achieved by just combining the existing alleles.
Kind of like sprinkling a bit of something on top and get a different result. So how do you choose when to stop the progress?
There's lots and lots of different ways to choose when to stop. In this particular example, I chose to stop when it got to good enough. It was 90% in the beginning, and then I got picky and said 99%. You could also stop when you've used some amount of CPU time if you're on a very hairy problem that's going to run a long, long time. Or you could sit there and watch it and press a stop button. Of course, meaning you have to build that ability into the program. Or perhaps some combination of those things. Like you could have it stop when it's gotten to some defined threshold of good enough, or it's run out of CPU time, or the user says, no, let's stop. Lots of ways you can do that.
All right. Well, thank you so much. We've run out of time. We hope to see you again in the next Nerdearla. And thank you so much for sending your talk.
You're quite welcome.
Vamos a una pausa y seguimos con el Track Nerd.
Vamos a nerdear.